Alright, so welcome to a video where I cover question 2 from the scholarship paper from 2012. So this is scholarship paper, Schol paper 2012. And question 2 on the scholarship paper is the organic chemistry based question. Again, part A tends to be just that little bit easier than, or quite a bit easier than part B. But still, it's a nice question nonetheless. So the context is ethidocaine is used as a local anesthetic. Its hydrochloride is marketed as Duranest. Structural formula for ethidocaine is given there. So this is the structural formula for ethidocaine. And what you're asked to do is you're asked to propose a synthesis for ethidocaine starting with 2,6-dimethyl-aniline, which is given to you here, 2-chlorobutane-1-ol, which I've circled in red, propan-1-ol, which I've circled in yellow, and ethanol, which I've circled in blue. And then obviously you need to list any appropriate reagents. You must include structural formulae for each step of the synthetic pathway. So what we want to do here is, first of all, the 2,6-dimethyl-aniline is this section right here. So we have that structure already formed, and we've formed that much of the compound. So we need to synthesize the remaining part, which is this part right here. And what I've done is I've identified the component parts and how we're going to make it up as follows using these colors. So 2-chlorobutane-1-ol, I'm going to use red for that. So let's get red here. So 2-chlorobutane-1-ol is going to be this compound, CH2OH, and then you're going to have, so basically 4 carbons in a row. Put your 4 carbons down, CH3, CH2, CH2, and then the chlorine is on carbon number 2. Remember, this is number 1, so this is number 2. So that's 2-chlorobutane-1-ol, and that should be just one hydrogen right there. So that's 2-chlorobutane-1-ol. Now what I've done is I've linked that up to where it's going to appear in the final compound, because we can change this to a carboxylic acid group with an oxidizing agent such as acidified permanganate or dichromate. And then that will account for the carbonyl carbon, which is right here in the compound. So carbonyl carbon is right there, and then that will come from the other carbon. So essentially this red section right here is coming from our 2-chlorobutane-1-ol. The chlorine allows us to introduce the nitrogen here. The nitrogen we're going to take from making an amine, a primary amine from our ethanol. So that will be a 2-step process. So our ethanol has the formula CH3COH, 2 hydrogens there. What we'll do is we'll take that primary alcohol and we'll make a primary chloroalkane or haloalkane, CH2Cl, and that will be performed using thionyl chloride, or PCl3 or PCl5, and that will get our chlorine on there, and then that's easily nucleophilically substituted with, if you use concentrated ammonia or alcoholic ammonia, then you'll get your primary amine, CH2NH2, and then this is in blue because this is going to fit in here in our final compound, so that nitrogen comes from our primary amine. So that's where we get that from, right there. And then that just leaves a 3-carbon alkane to stick on to the nitrogen from our aminoethane here. So that's aminoethane. So we use our propan-1-ol for that, and we just use yellow for this one. So the yellow color here is going to be for propan-1-ol, which is a 3-carbon alcohol. CH3, CH2, CH2, and if we take that, and what we want to do is again chlorinate it with something like SOCl2, thionyl chloride, or 3 or PCl 5, and we produce the this is going to be 1 chloropropane, CH2CH2Cl, and then that chlorine essentially attacks the ammonia center, or the amine center right there, and then that'll eliminate. You'll have loss of HCl, and you'll have this carbon will bond directly to the nitrogen, and that's what that bond is right there. So if you want detail for that, you can look at we can take a look at the answer that the NZQA guys provided. So if we scroll up here for a second, so you start off by taking your ethanol, so that's your ethanol right there. If you react with something like thionyl chloride, you make your chloroethane, and then you use concentrated ammonia, or you can also use alcoholic ammonia, and you get your 1-aminoethane, or ethanamide. Sorry, not ethanamide, 1-aminoethane, or ethanamine, that's the name, ethanamine. And then what you can do is, this is your propan-1-ol, and then you form your chloropropane. And you take those two compounds, you take this one plus this one, you join them together, and you form this intermediate substance. And then what you want to do is you want to take your 2-chloro-butan-1-ol, oxidize it. So oxidize it with dichromate, acidified dichromate in this case. You get your carboxylic acid group, and then your carboxylic acid group is what's going to target the amine group on the 2,6-dimethyl-aniline, and that introduces those two compounds. And then you use your compound. This was from our propan-1-ol, and this was from our ethanol. And then you join this compound with your intermediate substance there, and you get your final product of interest, which is your thiodecaine. So that's the detail there, the synthesis, which is provided by the NZQA answer scheme. Okay, so the first part of the question is nice. It leads you in nicely, and you think, oh yeah, I've done half the question, I'm doing okay. You move on to the second part, it gets quite tricky very quickly. So I had a lot of space to write there, I didn't use it. Part B. Okay, now part B is relying on a little bit of inference, I suppose is the word, where you have to use your previous knowledge from school, and also a bit of inference based on the little bit of extra information you're given here to figure out one of the final products in this series of unknown compounds. So we'll take our time and work through it. Let's see how we go. Okay, so part B of the question is all about drawing structural formulae to match up with the molecular formula that you've been given. The context for this question: acid anhydrides are derivatives of carboxylic acids. Their reactivity makes them useful starting materials for organic synthesis reactions. Acid anhydrides are formed from the condensation reaction between two functional groups. Now, if you look at an acid anhydride functional group here, an acid anhydride is this functional group right here. I want this as just black for now. So you have two carbonyl carbons, and then you have a linking oxygen like you'd have in an ester. And this is something that you haven't come across in level 2 or level 3 organic chemistry, but based on this bit of background context, you're expected to try and figure out how to make them. So they talk here about being derivatives of carboxylic acids. Well, if you look at this structure, hopefully you can figure out that it looks like it used to be one carboxylic acid which joined with another carboxylic acid. And so then when these two compounds join, there's a loss of H2O, which makes it a condensation reaction. And then, so that would lose, you could lose those two there to give you H2O. and then this oxygen links up the carbons to form your anhydride linkage. And now that's critical for the final part of the question. So I was going through this question earlier thinking, what is the relevance of that first opening paragraph? For the first 4 bullet points, there doesn't seem to be any relevance to it whatsoever, and then it was key to doing the last part of the question. Okay, so what I'm going to do is I have opened a new blank page, and I'm going to work through each of these isomers to just have a bit of space. So the first one, compound A here, has the molecular formula C6H10O3, and it has no enantiomers. So the key point here will be that it will have no chiral carbon. And a chiral carbon, remember, is a carbon which has 4 different groups. So maybe a methyl there, hydrogen, OH, and CH2 or something. So it has to have 4 different groups attached to it in order to make it an enantiomer. So what we're going to do now is we're going to go to a new page and we're going to try and draw out the possible isomers for compound A. So compound A is C6H10O3. So what I like to always do is just put down a single row of carbons. So 1, 2, 3, 4, 5, 6. We have to get 3 oxygens in there somehow. So we can either use alcoholic groups, carboxylic acid groups. We could use that anhydride group if we wanted to, but it's not needed in this case. But it is a case of trial and error, and what I'm going to show you is there are two actual possible isomers you can draw for this. There's this one right here. So I was doing this morning, and I figured this one worked pretty well. So there's no real way to teach how to do structural isomers from molecular formulae other than to put them on paper and then see that they match up to the expected criterion. So this is what I came up with initially, and so let's just check that over. So carbons, 1, 2, 3, 4, 5, 6 carbons, so we have C6. Hydrogens, we have 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. So that seems to fill the criterion, but it's the wrong answer, because when you go on to try and do compound B is a reaction of compound A with acidified potassium dichromate. And as you can see here, we already have our carboxylic acid group on that there, and to form another carboxylic acid is not possible. So it's not possible to oxidize that particular compound I drew with dichromate, for example. So the actual isomer we want to be drawing is this one. So it's C double bond O, CH2, CH rather. So let's do that again. Didn't start that off the right way. So it's CH double bond O, CH2, CH3. This OH group now is important. CH2 and then CH double bond O. So it's an aldehyde essentially, 2 aldehyde groups on either end. So it's like a dialdehyde. They're aldehyde groups, and that matches up with the C6H10O3 as well. Now, this does work for B, because B's molecular formula, if we go back to the question, says compound B, so we've got compound A. In reaction of compound A with acidified potassium dichromate, solution results in compound B. Now, acidified potassium dichromate, an aldehyde being oxidized further to a carboxylic acid. So we have our aldehyde here, our dialdehyde, if you want to call it that. And what we're doing is we're oxidizing both of those aldehyde groups, further oxidizing them to carboxylic acid groups. So we're using acidified potassium dichromate, so I'll just write in Cr2O7 2- with H+, and that's for both instances here. And then we end up with C double bond O bonded to OH, CH2, C, CH3, OH, CH2, C, double bond O bonded to OH. And that molecular formula should be C6. So let's just check that. 1, 2, 3, 4, 5, 6. H, 10. 1, 2, 3, 6, 7, 9, 10. And then oxygens, we should have 1, 2, 3, 4, and 5. So C6H10O5. So that's compound B. So compound A was this. Compound B is this one. We scroll on down again. So now we're at compound B. Now what happens? We go back to the question. So we have compound B. Reaction of compound B with anhydrous zinc chloride in concentrated hydrochloric acid. This here is Lucas reagent. That's known as Lucas reagent. Okay, produces compound C, and you can see there's a chlorine on there. So compound C is it's either a chloroalkane or it's an acyl chloride, one of those. So what we have here is the key point now is this OH group is being attacked by the Lucas reagent, ZnCl2 solid, which has been dissolved in concentrated HCl. And then you get a substitution. So this is a nucleophilic substitution of the chlorine for the OH group. And then you result in this compound C, which is OH, OCH2, CCH3. You have a chlorine on there now instead of the OH group. C double bond O bonded to OH. The molecular formula for that then for C should be C6. So 1, 2, 3, 4, 5, 6. H 9. So 1, 3, 6, 7, 8. Let me just count them again. So 1, 3, 6, 8, 9. So we have our 9 oxygens. 1, 2, 3, 4, O4, and Cl. And that matches up with compound C. So we've done compound C. We still keep going. All right, back to the question. Compound C we have. Compound C reacts with alcoholic potassium hydroxide, followed by acidification to produce compounds D, E, and F with that molecular formula. Compound D does not have stereoisomers, but compounds E and F are geometric isomers of each other. So the key point here is your reagent is alcoholic potassium hydroxide, so KOH alcoholic. So this is an elimination reaction. And with elimination you can have a major and a minor product according to Zaitsev's rule or Zaitsev's rule. Some teachers call it the anti-Markovnikov rule. And that should account for 2 of your isomers. And then the other isomer is just is the one which doesn't have geometric isomerism. Or rather, the other isomer is just the geometric isomer of one of the 2. So we go back here, and what we're doing now with C is we are going to eliminate. Okay, so looking at C, we want to eliminate the chlorine, and therefore if we eliminate it, we must be also taking with it a hydrogen. So Zaitsev's rule, you must take the hydrogen from the carbon with the least amount already. So you could take it from either here or here, it doesn't matter. So one of the compounds is going to be OH, C double bond O, OH double bond C, CH2, C double bond O bonded to OH, and then CH3 and plus HCl. You took one hydrogen from here, plus the chlorine gives you that HCl. This compound is the major elimination product. Okay, the minor elimination product is going to be this one. You take the hydrogen from this one here, which was rich in hydrogen, so that's CH2, plus your HCl. That's your minor product. Okay, and then there's one other product they said to talk about. So the other product is the geometric isomer of this one right here. Because if we rewrite this compound, just delete that for a second, and we rewrite it where the hydrogen is up here, well, this would be this, and then the trans isomer is going to be where that hydrogen is down there, and then the CH3 is up here, and the rest of the compound is the same. So that would be the trans isomer. So to name these now, so this is compound F, this is compound D, and just to go back for the evidence for that, go back to the exam paper. So compound D does not have stereoisomers, so that was compound D right there, no stereoisomers possible, so no stereoisomers, as we just demonstrated, so no cis and trans for compound D, so that's compound D. Compound F and E then, how do we know this one is F and this one is E? Back to the exam paper. Compounds E and F are geometric isomers of each other. Now, when compounds D and F are heated, two different compounds, G and H, with the molecular formula C6H6O3 are produced. Compound E does not react on heating. Okay, if we look at compound E, alright, so compound D, we're told to basically ignore that now, and we're going to just take F and D. Now this last part of the question, I'll get a new page for this. This last part of the question is really just pure inference based on the little bit of new knowledge that you're given at the start of the question. So what I'm going to do is I'm going to rewrite the compounds D and F, because when you heat them, they form these compounds G and H, and we're going to show you how that happens. Okay, so let's look at the final part of the question. When compounds D and F are heated, two different compounds G and H with the molecular formula C6H6O3 are produced. Compound D does not react on heating. So this really is the sting in the tail for this question, and it brings you back to this point they made at the beginning here, that acid anhydrides are derivatives of carboxylic acids, and the reactivity makes them useful starting materials for organic synthesis. So they're formed from the condensation reaction between two functional groups, and we postulated a scheme for that at the beginning here, with two carboxylic acid groups coming together with the elimination of H2O, which is a condensation step. So this is what happens here. I've laid the question out neatly for us. So this was isomer D, and I've deliberately used blue and red for two parts of the compound, and then this is isomer F, again using red and blue, and all we're doing is heating these things. So what essentially happens here is I'm going to call this self-cyclisation. Self-cyclisation. I don't know if I just made that term up or if that is the actual official term for this process. So basically what happens is one carboxylic acid group attacks the other carboxylic acid group, and then with the loss of water. So if we lose this hydrogen here and this OH group, then that accounts for the water being lost. And the same thing happens on this side. This carboxylic acid group attacks this one with the loss of water. So that's your condensation. That's your condensation reaction. Two relatively large molecules joining together with the loss of a relatively small molecule, in this case water. So what we get is when we join, the compound basically bites its own tail, we're going to get these particular cyclic compounds. So we're going to get C double bond O up there, CH2, and then we're going to get C double bond CH3, and then from that we're going to have our red section, which was CH2, C double bond O, And then this here, this is our acid anhydride group, which brings us back to the beginning of the question. And then the same on the other side. So this, by the way, this is compound G. Let's just check if that's the right one there. So two different compounds, G and H. All right, so they didn't tell you to necessarily say which one G came from and which one H was. This is compound G or H. For this one over here, same situation. I'll draw the red part first. So C double bond O, CH2, and then your O oxygen goes up there, and back to the blue. C double bond O, bonded to CH, double bond C, CH3, and then back to there. In both cases, you get the loss of water. I'll just do part of it in blue, and then the other part in red. Okay. So that is also your acid anhydride group right there. So that's my complete answer for question 2. As I say, sometimes in these questions, are you expected to go and read up on all the other possible organic chemistry questions that can happen? The answer to that is no, because there are hundreds of schemes outside of level 3 organic chemistry that you could read up on. You're expected to come back to first principles of what you learned just in school to figure these questions out. But it's no harm to do a little bit of extra reading around some of the more common reactions that happen with the functional groups that you've studied in school. So that's question 2 from the 2012 scholarship chemistry paper.